Hello. Let me start the recording and just say that like today we have Salva. I hope your name is pronounced like that.
Correct.
From Fabian's group actually. Fabian is the guy called Professor för algoritmen och komplexitet. And today is going to be congest algorithms, and now I give it over to Salva.
Okay, thank you, Yara. I hope everyone can hear me well. So my name is Salva Fauer, and as Yara said, I'm a PhD student at the University of Freiburg, Germany. So today I will present to you a paper that appeared in OPODIS at the end of last year, 2020. It's a joint work with my supervisor, Fabian Kuhn. The title says it all. I'm gonna talk about how one can approximate the problem of minimum vertex cover in bipartite graphs in the distributed congest model. So let's begin. Okay. The plan of the talk is the following. I will first introduce what the minimum vertex cover is and present our first simple result. Then I will talk about the state of the art of the problem in the distributed setting and our main contributions. In the next two sections, I will go further in details and explain the key ideas and algorithms that led to our main result. And then I will conclude with some open problems. Okay, so let's begin. On the minimum vertex cover problem, we are given an arbitrary graph. And here we consider all our graphs to be unweighted. And the goal is to find a vertex cover with minimum cardinality. So what that is, it's a subset of the nodes that contains at least one node from every edge. So it covers all of the edges of the graph. And this subset should be of smallest possible size. So for example, the yellow nodes here on the graph make up a minimum vertex cover of that graph. All of the edges are covered by at least one yellow node, and there's no vertex cover of size 1. So this is a minimum vertex cover. Okay. Now, since the minimum vertex cover problem is closely related to the maximum matching problem, and we will use matching algorithms later on, we recall what it is. So we are given an arbitrary graph, again, consider it unweighted. The goal is to find an independent set that is pairwise non-adjacent set of edges with maximum cardinality. So for example, the yellow, excuse me? Okay, so for example, the yellow edges here make up an independent set, so they don't share any common node, and they are of maximum size too. Now, we will also mention maximal matching. This is a matching such that no more edges can be added to that matching. So if you add an edge, then it's no longer a matching. And on the side note, a maximum matchings are maximal, but the other way around is not necessarily true. Okay. Now, we study the distributed complexity of our problem in the standard congest model. In this model, we have a network. Think of a computer network. And it is represented as an undirected graph on n nodes. So each node or vertex, these mean the same thing, they represent a computer or a machine. And each node will have a unique order of log n bit identifier to it, so a special identifier. And the time or the computation of the algorithm here proceeds in synchronous communication rounds. So when I talk about time complexity, I mean round complexity. So how many synchronous communication rounds do I need for my distributed algorithm to output a solution and terminate? In each of these communication rounds, every node can do arbitrarily local computations. So they could be large, exponential time even. And another thing, each node can send over an edge to its neighbor, a message. But this message should be is restricted to order of log n bit. So the size of the message is restricted. And what happens is that at the end of this distributed algorithm, every node should know its own part of the output. So if we are solving the minimum vertex cover problem here in the network, every node at the end should know whether it belongs to the vertex cover or not. So it's in the solution or not. Now, because we will mention the local model and the state of the art next, let's recall what it is. The local model is the less restricted version of the congest model. It's defined exactly the same as the congest, with only one difference, is that nodes can exchange messages with each other, and these messages can be arbitrarily large in size. So there's no bound on the size of the messages. So you notice that when working with the local model, we don't run into the trouble of congestion, like we might in the congest model. Okay. Now let's present our first simple contribution, which is a linear time algorithm to solve the exact minimum vertex cover problem in bipartite graphs. And things are going to be implemented in the congest model. So we have a known fact that in general graphs, a minimum vertex cover is at least as large as a maximum matching. Knish's famous theorem tells us that the equality holds if the graph is bipartite. So the size of the maximum matching is the same as the minimum vertex cover if you have a bipartite graph. And in the proof of the theorem, a way of constructing a minimum vertex cover given a maximum matching is provided for us. So a direct implementation of this constructive proof will give our first result. And this is what I'll be doing. I will briefly present the implementation because it's going to serve, the ideas serve as the basis for our key algorithm, which is used in the main algorithms later on. So let's do the implementation. We're given a bipartite graph, and we assume the bipartition of the nodes of the graph are given into sets A and B. The algorithm goes as follows. We first compute a maximum matching M star for this bipartite graph. And in the distributed setting, we know how to do that fast. There is an algorithm that runs in order M star log M star by Ahmadi Kun and Ashman. It runs in the congest model. And then a vertex cover of the same size of this maximum matching will be computed as follows. So let's first consider the set of nodes A0 to be the set of unmatched nodes in one of the parts of the bipartition. So I choose A. And by unmatched nodes, I mean nodes that are not connected to any matched edge. Okay. And if at some point in the talk I say free nodes, I also mean unmatched nodes. Okay, so I have my set A0, and then the goal is to compute set L. Set L is the set of nodes in A union B that are reachable from a free node in A0 over an alternating path. So alternating path, I mean a path that alternates between edges in the matching and edges outside this maximum matching. And this set L can be computed easily by doing a parallel BFS exploration starting from free nodes in A0 over alternating paths. So if I demonstrate what I mean, so I'm doing my parallel BFS right now over alternating paths. So these nodes here, all of these that have been hit by the BFS is in L, are in L. This parallel BFS exploration can be done in order M star rounds, simply because the longest alternating path is going to contain at most all of the matched edges. So now the algorithm will eventually output C star. C star is going to be our minimum vertex cover. It's going to be defined as follows. So it's going to take in all of the nodes in A that have not been hit by a BFS search. So for example, these nodes here. And it's going to take from B all of the nodes that have been hit by a BFS search. So the gray part here. Okay, then it's not hard to show that C star is going to be a vertex cover that contains exactly one node from every matched edge in M star. And we have the known fact that the size of the minimum vertex cover is at least that of the maximum matching. So we would deduce that C star is going to be a minimum vertex cover of size equal to that of M star. And we can do this in order opt logged opt, or order M star log M star. Let's say it's dominated by the computation of the maximum matching, which is equal to that by Knish's theorem. We know these two are equal because opt here represent the size of the minimum vertex cover of the graph, which is the same as C star, right? Okay. Good. So now let's move on to talk about the state, what we know about this problem in the distributed setting and our contributions there. Now, when studying the distributed minimum vertex cover problem and related optimization problems on graphs, the focus has been on studying the locality of these problems. So how many synchronous communications round do I need to take to solve or approximate the problem in the local model, the locality of the problem. So less work has been done in the congest model. But in all cases, let's see what we know in both these models. For the local model, for both the general and the bipartite graphs, solving MVC, so minimum vertex cover, exactly takes theta of d rounds. D is the diameter of the graph. And this is because on one hand, every problem in the local model can be trivially solved in diameter time. So one way of thinking about it is that every node will gather the topology of the graph, all the information in the graph in order of diameter time that it can do, and then it would brute force the solution locally. Each node would solve it locally. So we need order of d rounds. Now on the we can solve it in order of d rounds. On the other hand, we need diameter rounds because the problem of finding an optimal vertex cover on even paths is equivalent to finding two coloring on even paths. And there we know that solving two coloring on even paths needs diameter time, or even solving two coloring on paths takes diameter, needs diameter rounds. So this would make the complexity here theta of d in the local model. As for the congest model, for general graphs, the best known algorithm is an order opt squared by Ben-Basat, Kuwar-Berishu, and Schwartzman. Opt here, I will always mean by it the size of the minimum vertex cover. And we have an upper bound, so this is close to tight, in tilde omega n squared. So tilde here is hiding some polylogarithmic factors. This is given by Sensor-Hiller-Khoury inputs. After the bipartite case, we have seen how we can solve this in order opt-log-opt just by the direct implementation of Knish before. And there is an existing lower bound given by Ahmadi, Kuhn, and Ashman until the omega d plus radical n. This lower bound actually is proved for the maximum matching problem, but the same argument will follow for the minimum vertex cover problem. Okay. So we want to do things faster, and with approximation we might. Indeed, one can simply find a two approximation vertex cover solution by first computing a maximal matching and taking both nodes of every matched edge for the vertex cover. And I've said before that for maximal matchings, we know there are algorithms that computes maximal matching fast in the local and the congest, randomized and deterministic. Hence, we care about better approximations, the 1 plus epsilon approximation. And we always think of epsilon to be a sufficiently small constant, so between 0 and 1, okay? In the local model, Ghaffari, Kuhn, and Maus have shown that not just approximating MVC, but also other covering and packing problems can be done in order polylog n over epsilon for general graphs, so this would work for bipartite. And on the lower bound side, due to the work of Goose and Swamila, it was further proved that there exists no sublogarithmic time approximation scheme for vertex cover for bipartite graphs. And this is even for bipartite graphs of maximum degree 3. So this lower bound would work for the general too, and for congest. Now, one can improve this lower bound if you consider the same bipartite 3 regular graph on which Goose and Swamila, from the previous lower bound now, showed that getting a 1 plus epsilon approximation is hard on. So for special choice of epsilon. And if you take the same bipartite 3 regular graph where you can't approximate things fast on, and replace each edge of this graph by a path of odd length, say in order 1 over epsilon. Now, along with some other observations, one can prove that on this new graph, which can still be seen as bipartite, we will need at least omega log n over epsilon rounds to get a 1 plus epsilon approximate MVC. So for bipartite graphs that are not necessarily regular, we need this many rounds. This would also follow for the congest model, for the general and the congest model. Now, the distributed complexity in the local model is kind of understood well, but there has been recently increased interest on understanding the complexity of these problems of the approximated MVC, for example, in the more restrictive congest model. And however, for a better than two approximation, nothing faster is known than computing the exact solution that we have seen from before in both the general and the bipartite graphs. Also, we know that all of these algorithms here for the local model quite heavily exploit the power of the local model, and thus cannot be directly implemented in congest. Okay, so we need to do something smarter. So in this work, we focused on the bipartite case and asked ourselves, can we efficiently find a good approximate minimum vertex cover in the congest model? And yes, we can. We can do that randomized and deterministic. This was our contribution. We're able to do things in polylog n over epsilon. This is fast. And for the randomized case, it's even faster. And for a fixed epsilon, this should be the same, epsilon, it would match this improved lower bound also. Okay, so let's see how we can achieve these results. We will first show how we can approximate the problem in time linear in the diameter, both randomized and deterministic, and then how we can use that to get faster algorithms. Now, the core of our time linear and diameter algorithms is the method of to transform an approximate maximum matching to approximate minimum vertex cover in order d plus k rounds on bipartite graphs, of course. Now, I always consider k to be an integer parameter. So my goal here would be a 1 minus 1 over k approximate maximum matching to a 1 plus 1 over k approximate minimum vertex cover. This matching should have an extra property, which is that it has no short augmenting path. So what do I mean by short augmenting path? I mean, a short augmenting path is an augmenting path of length at most 2k minus 1 for a choice of k. And what do I mean by augmenting paths in this setting? It's just a path that starts and ends with unmatched nodes and alternates between unmatched and matched edges. Okay, now, of course, not of course, but we know by a result of Hopcroft and Karp that if you have a matching with no short augmenting path, so no length of at most 2k minus 1, then your matching is 1 minus 1k approximate, but the other way around is not necessarily true. Okay, so let's show how our approximation scheme works here by adapting the constructive proof of Kunish's theorem that I just mentioned earlier. Okay, so to simplify things, let's work on an example. And first, let me take k to be an integer parameter. Here, I'm going to choose k to be 2. Again, we have a bipartite graph. If the bipartition is given into A and B, great. If it's not, then I can easily compute the bipartition via constructing a spanning tree in order of diameter rounds. And I will need the spanning tree later on in the algorithm. That's why I mentioned it. Okay, now we're going to assume that we are given a matching that has this guarantee that no short augmenting paths exist. So in our algorithm, so in our example here, any augmenting path is going to be of length at least 5, right? Okay, and then just like before, we're going to define A0 to be a set of free unmatched nodes in A. And then the algorithm is going to go as follows. It's going to do some partitioning to some nodes of A and B into BI and AI. I is going to be from 1 to k. How I'm going to define BI, it's going to be the set of nodes in B such that it's reached over an alternating path from a free node in A0. And this alternating path is going to be of odd length to I minus 1. All right. And an AI is going to be defined in a similar way. It's just nodes in A, reach from here over an alternating path, but the length is going to be even, and it's going to be 2i. Okay, so let's demonstrate what I mean by this construction in our example. And to do this construction of the BIs and AIs, I did not say, we can do this in the congest model by running the first 2k iterations. So I want 1 2k, 1 2k, so 2k iterations of parallel breadth first search starting from A0. And then depending on whether the node is in the odd or even level iteration, it can know whether to join BI or AI correspondingly. Okay, so for this example, I'm gonna do just the first 4 iterations of parallel BFS. Let's see how things work out. So this is gonna be my B1. We're doing it over alternating paths. A1, B2, and A2. Okay, I just need the first 4. Notice the nodes that have not been hit by ABFS is not in any of the BIs or AIs. Okay, the time required to do this parallel BFS is going to be order of k rounds. Now, the algorithm is going to continue to define I star. This I star is going to be from, it's going to be either from the set 1 to k. And it's defined in a way that where BI is going to attain its minimum. So the I that where the BI is minimized. So in this example here, I star is going to be B2 because B2 is the smallest among the BIs, which is just 2, B1 and B2. Okay. And then computing I star in the congest model can be done in order D plus K rounds. We can use this parallel BFS spanning tree I talked about from the bipartition for finding the bipartition to perform a simple pipelining scheme. So that at the root level, we can compute all of the counts of those BIs, and then the root can determine the index I with the smallest such set. Now, if there were more than 1, then the root can arbitrarily pick any. That would still work. Finally, for step 5, the algorithm outputs the set Ci star. It's going to contain all of the nodes in A from that are not in A0 up to AI minus 1. So these from here, from AI star until the end. And from B, it's going to contain all of the nodes that are from B1 up to BI star. Okay, so this is going to be the gray part, for example, here is going to be my Ci star. This can be also done in order of D rounds. The root of the tree can broadcast I star when it computes it to all of the nodes via this BFS spanning tree in time order of D. And then the nodes can decide whether to join Ci star or not accordingly. Therefore, the overall time complexity of the algorithm is going to be dominated by this, by finding I star in order D plus K. Now, to prove that Ci star is our desired approximate vertex cover, we first have to show it's a vertex cover. Actually, every edge, if you notice, is incident to at least 1 node from Ci star, so from the gray part, right? If there's an edge that is not covered, then it's gonna have to be connected to some node on the top left level here in the A, for example, this node, to another node in B from the bottom right, outside Ci star, for example, this node. So such a red edge won't be covered, but this cannot exist. If this edge was matched or not, it cannot exist by the construction of the BIs and AIs. So this node would have to be somewhere in the BIs. Hence, this node cannot, this edge cannot exist, and Ci star is a vertex cover. Now, to finally show it's an approximate vertex, a 1 plus 1 over k approximate vertex cover, we need the following 2 observations. First, we notice that each set AI, the ones in here, are going to, in size, they're exactly the set of nodes that can be reached over matched edges, over the matching edges from nodes BI. Okay, by the construction we have done. So each AI is going to be equal to BI. So A1 is going to be the same as B1, A2 is the same as B2. And the second observation is that all the nodes in the BI, so from B1 up to BK, so in particular from B1 to BI star, they are matched nodes. So for example, B1 here and B2, they are all matched nodes. Why is that? Because if they were not, then there will exist a short augmenting path coming from A0 to one of those BIs, and this cannot happen. Our matching has no short augmenting path. Okay, and since BI star is the smallest of the BIs and we have k of them, then obviously it's going to be at most k fraction of the size of the matching. So using these two observations, simple calculations will give us that Ci star is a 1 plus 1 over k approximate vertex cover. Okay, so from here, there are actually two challenges that will remain for eventually getting faster polylogarithmic time algorithms. The first challenge is that, okay, I've been assuming this matching with no short augmenting paths all along. So I want to compute it and I want to do it fast in the congest model. So can we do that? And the second challenge is that if we do that, then if we fix the first challenge, we have an order d plus k algorithm that solves our problem. But the diameter might be still large, so I want small diameter to get faster algorithms. So let's work on with the first challenge. If I solve the first challenge, I would show you how to get linear and diameter time algorithms, both randomized and deterministic. Okay. So if we allow randomization, then there exists a congest algorithm that gives a matching with no short augmenting path. This exists, given by Lotker, Patchamir, and Petty. And this is with high probability. So we compute, we use their algorithm, and then we can run our Q approximation scheme. And then we would get a time linear and diameter algorithm that solves our problem with high probability. So for fixed K, for example. Now, for the deterministic case, we can run a polylogarithmic time approximate maximum matching algorithm in the congest model, given by Ahmadi, Kuhn, and Oshman. This is the complexity. But this approximate matching does not guarantee us that it has no short augmenting paths. This is what we want. So how do we resolve this? Okay, the high-level idea is to first remove a small number of nodes S1 from this graph. Okay, and I want to remove this. Upon this removal of the nodes, I want my remaining graph to have no short augmenting path. And then one can see that we can apply our key approximation on scheme on the remaining graph. And then we can get an approximate vertex cover there, which is going to be all the nodes are going to be in S2. And then we can add those removed nodes S1 to S2 to output C, and then one can show that C is going to be what we want, our 1 plus 1 over k approximate MVC. But the problem of finding a small set of these nodes to remove such that we get rid of all the short augmenting paths is the tricky part. And how do we do that? It's going to be reduced to the minimum set cover problem. There, we can approximate this problem by solving it using an efficient algorithm in the congest model. So let me explain this idea a bit more on how one can see the problem of removing a small number of nodes from the graph such that we get rid of short augmenting path as a minimum set cover problem. So let's consider a short augmenting path. It's of length at most 2k minus 1, just like here in this figure. And the idea is that from this and every short augmenting path, if I'm able to remove at least one node from it, then I get rid of the short path, right? But we want to take care that we don't create even shorter augmenting paths by doing so. We don't like that. So for example, if I choose this node here to remove, this node is a matched node. So a matched node, I mean it's connected to some matched edge. Then by default, this matched edge here is going to be removed, for example. And now this node is going to be free, unmatched, because it's not connected to any matched edge anymore. So it's going to be unmatched. And now I create a shorter augmenting path. I don't want that. So instead of doing this, let's try and remove from every short augmenting path at least one matched edge. And if I remove a matched edge, it means I'm going to remove both of its endpoints on the way. These are going to be included in my vertex cover at the end. So if you remove this match S, for example, I don't create any shorter path, and the short path is already gotten rid of. Great. Also, I would like to allow removals of unmatched nodes of every short path that are at the endpoints of the path. So if I remove an unmatched node also, this would get rid of the short path and it would also not create shorter ones. So now the call is here clear. We want to remove from every short augmenting path the least possible number of matched edges and free nodes. So matched edges, I also remove their endpoints. Hence, this would be a minimum set cover problem. The ground set would be the short augmenting path, and each set of the subsets will represent a short augmenting path that the corresponding matched edge or free node covers or contains. And now the objective is to find a subset of matched edges and free nodes contained in these short augmenting paths such that they cover the ground set. They cover all of the short augmenting paths. I'm saying too much augmenting paths right now. Okay. So now the solution of this set cover problem that I just mentioned would give us the set S1. This would be the solution. The nodes to be removed and then to be added to my vertex cover I'm constructing. And it turned out that simulating a version of the greedy set cover algorithm and the congest model is enough to solve this problem. I can prove with that it's small. And by a version of greedy, I mean each greedy step is just relaxed to a factor of 2. So instead of picking a free node or a matched edge to cover the most short augmenting path, I wanted to cover at least the most short augmenting paths. Now, unfortunately, I don't think I have time to explain the simulation and the congest model. It's a little bit tricky, or the analysis, but I do have slides prepared, so if anyone's interested at the end, or I can refer you to the paper, of course. So we've solved our problem deterministic case. We can run now this algorithm here that gives us an approximate matching. And then we can get rid of the short augmenting path by solving set cover, like I just mentioned before. Now, I just want to mention that this matching here for the deterministic, it's not going to be a 1 minus 1 over k. It's going to be a better matching, but that's fine. The approximation, the 1 over k is going to be smaller. Okay, so I do this thing. I get rid of short augmenting path. I run my approximation scheme of the remaining graph. And I would get a polylogarithmic time, no, I would get a time linear in the diameter algorithm deterministically. So I want my diameter to be small now. For the second challenge, we're going to resolve this in the following. If we resolve the second challenge, we're going to get the polylogarithmic time, as I said, algorithms. Okay, so how do we resolve this problem? We're going to decompose the graph into clusters of small diameter. And to do that, we're going to adapt fast existing clustering algorithms. The randomized, there's a clustering algorithm by Miller, Ping, and Zhu. For the deterministic, there's the network decomposition by Rogen and Ghaffari. So we adapt those, and then we solve the problem inside of these clusters, because now we have small diameter. But this clustering that I want, I want it to be with some specific properties. This will help us deal with the edges between the clusters that might be left uncovered. Now, I'm going to explain how we can get such a clustering with these specific properties and what I mean by that, by giving a simple, nice general framework that will work for both the deterministic and randomized cases. And this will give us the polylogarithmic time algorithms I'm talking about. That will be our final algorithm. Okay. So again, we're given a bipartite graph G, let's say. We start with an empty set C. This will be our approximate vertex cover that I'm going to be constructing. And then the first step is to run a maximal matching on this bipartite graph. Again, we have fast algorithms for that, deterministic and randomized and the congest. Okay. So now we're going to compute a low diameter clustering of G with these specific properties. We do that by adapting the existing low diameter decompositions, but I'm not going to explain in details how. But what I mean by this, what I mean by specific properties, I'm just going to mention 2 out of 3 of the main properties of this clustering. First, I want it to be 3 hops separated So this means that any two nodes in the clustering, whether in the same or different clusters, they're going to be 3 hops away from each other. So for example, if I take this node and this node here, it's 1, 2, 3, 4, 5, or 1, 2, 3, okay? At least 3 hops away. And the second property is I want the match edges that are outside the clusters, I want them to make up a small fraction of the whole maximal matching of the graph. So for example, these black edges, these are my matched edges that are outside the clusters. And in this clustering, I want them to be a small fraction of the maximal matching, okay? So what I'm going to do is I'm going to add all the unclustered matched nodes to C. So by unclustered, I mean this node is completely outside and it's a matched node connected to a matched edge. So who are these unclustered matched nodes in our example? So for example, these black nodes here. Okay, so these are added to C. Now, if you think about the edges that are completely outside the cluster, so both endpoints are outside, so this one, for example, here, then all of these are covered, right? Because we have a maximal matching. And this means that any edge, so the edges outside, think about those, has to have one of its endpoint a matched node. And we take those matched nodes in step 3. So this means we cover all of the edges that are completely outside. How about the edges that are on the boundaries? For example, this edge here, that's not necessary, that's not covered. This is not a matched node. So how do we resolve this? We extend each cluster now by at most 1 hop to include all of these uncovered edges on the boundaries. Now, note that this will only grow the diameter of each of these clusters by at most 1 hop, and we would still have small diameter. Okay, so let's try and extend these clusters here on our example by 1 hop. Okay, so I'm just including edges that have not been covered on the boundaries. Now, notice that since our clusters are 3 hops separated, then our extended clusters are still pairwise disjoint. They won't overlap. So with this extension, no 2 clusters are going to fight over to include the same node because they are 3 hops separated, right? And hence, all of the edges that are uncovered now are going to be inside all of these extended clusters. Good. So now, because we have low diameter inside these extended clusters, we can apply our linear and diameter time algorithms. Okay, we're going to do them there. And we're going to find approximate MVC for each of these extended clusters. And then this will be an approximate solution for the union of the all extended clusters. So what we do is add them to C. And then one can now show choosing the right parameters for these approximations here and the small fraction that of the matched edges that I want to be outside, that this C here is going to be make up a 1 + 1 over k approximate MVC of the original graph. And now we can prove that this general framework works for both randomized and deterministic, and it will be fast. Sorry about this. I'm just showing you the complexities here. For the maximal matching, this is the randomized algorithm by Luby, and for the deterministic, we have an algorithm by Fisher. It's also polylog. And for computing low diameter clustering, I said we adapt those network decompositions. They're also polylog. In the 5th step, we apply our linear and diameter algorithms. We know diameter is going to be small in the clusters, so we still have polylog n over epsilon. And then for both the randomized and deterministic case, we get order polylog n over epsilon. So algorithms. So this general framework solves our problem fast. We can cross off challenge 2. Good. And so to conclude, we have seen how one can use these algorithms, the linear and diameter time algorithm, together with existing adapted low diameter clustering techniques, to obtain a polylogarithmic time approximation to approximate the minimum vertex cover problem in bipartite graphs. Okay, I think now we can conclude this presentation. I hope I'm not. Okay, so if we recall, for exact MVC, there's this lower bound for computing an optimal vertex cover on general graphs. we can do better than n squared, or hiding some logarithmic factor for the congest model. So how about approximation? An open problem is still out there. Is it possible to approximate MVC within a factor smaller than 2 fast? We don't know how to do that, or even to understand which families of graphs is this possible. I mean, we're working with an NP-hard problem here, and if you think about the local model, we exploit the power of the local model. So these two are still open. This is an open problem still. And just on a side note, all of the results you've seen here can be generalized to the weighted case. So we can get fast algorithms to approximate the weighted minimum vertex cover in biprotect graphs. Okay, I think that's it for me. I would like to thank everyone for their attention. Okay.
All right, thanks a lot for the talk.
Welcome.
Now everyone has an opportunity to raise a question. Usually the protocol has been that people can just unmute themselves and ask, and it has worked with the audience of 20 people. So everyone is now welcome to just